So let me welcome you to the 13th Flow Seminar. My name is Samuel Horvat, and together with Peter Tarik, Virginia Smith, Avralin Bellet, and Dan Alistair, I'm one of the co-organizer of Flow Seminar. For those of you who are attending for the first time, Flow Seminar stands for Federated Learning One World Seminar, and it was created as a global online forum for the dissemination of the latest scientific research in all aspects of federated learning. This includes both theory and application, and areas such as distributed optimization, learning algorithms, privacy, cryptography, personalization systems, and hardware. For today's talk, it's my great pleasure to introduce you our speaker, Tian Li. So Tian is a third-year PhD student in computer science department at Carnegie Mellon University, working with Virginia Smith. So prior to CMU, she received her BS in computer science and BA in economics from Peking University in 2018. She's broadly interested in large-scale optimization, fairness and privacy in distributed learning and data-intensive systems. And today she's going to tell us about learning in heterogeneous networks, optimization and fairness. Yeah, so thank you for joining us, and Tian, stage is yours.
Okay, hi everyone. Thanks for inviting me here. And I'm Tian from Carnegie Mellon. So today I'm going to be talking about some of our works on federated learning. And in particular, I will focus on the optimization and also the fairness aspects of learning in heterogeneous networks. So federated learning is privacy-preserving training in heterogeneous and potentially massive networks. And those networks can be a network of remote devices like cell phones, or it can be a network of isolated organizations like hospitals. And you can imagine that training statistical models in these scenarios has many applications like anomaly detection in IoT devices, adapting to pedestrian behavior on autonomous vehicles, and personalized healthcare on wearable devices, and performing predictive maintenance for the sensor networks that are deployed in those industrial machines. And so a typical objective for federated learning is to find a global model W to minimize such a loss function, which is a weighted average of the local loss. And Fk is the loss on the kth device, and Pk is a predefined weight. And throughout this talk, we assume that we're in a typical centralized training setup where there's a central server and there are a bunch of devices communicating model parameters with the central server periodically to learn a global W. And in this setup, there exist a lot of challenges. And first, the systems, the entire systems are heterogeneous due to the variable hardware, the variable network connectivities, the battery power of these devices, and so on. And also the user data generated from each device can be highly non-identically distributed. So they're not coming from the same distribution. And this statistical heterogeneity issue can affect the training pipeline a lot. And also communication is extremely expensive in such settings compared with traditional distributed machine learning in data centers. And also privacy is a big concern since transmitting model parameters can still reveal sensitive user information. And in this talk, we'll mainly focus on the first two heterogeneity challenges. So I'm going to talk about how heterogeneity affects optimization methods, and then the fairness and how heterogeneity could affect the fairness of the quality of service we provide in federated networks. So the first question we ask is, how does heterogeneity affect federated optimization methods? And a very popular optimization method in this setting is federated averaging, or Fed average. The way it works is that at each communication round, the server will randomly subsample a subset of devices and send the current global model WT at the tth iteration to them. And then each selected device K will update the local models by running some amount of local computation, for example, epochs of local SGD to optimize their local subproblem, and sends the new local model back to the server. And the server aggregates those local models to form a new global model, T+1, at the next communication round. And this algorithm is simple, but it's quite robust in practice, especially in those non-convex problems, such as deep neural networks. And however, it can diverge in heterogeneous settings. And so first, in statistically heterogeneous environments, simply averaging local updates can cause the method to diverge. This can happen when you run too many local updates, because those local updates are going too far. They're optimizing towards the optima of the local devices, which are quite different from the global objective. So if they're going too far away from the initial starting point, it's likely that they will perform badly after naive aggregation. So just to show an example here, when the number of local epochs is equal to 1, fat average will converge, but when E is increased to some large values like 20 or 50, it starts to diverge. And also the issue of systems heterogeneity can also make things worse. And since the system's conditions vary a lot across the network, stragglers are a critical issue. And in fat average, it simply drops the slow devices, which cannot finish the local training before the given deadline. So this may also hurt the training procedure when there are many stragglers, because you're implicitly increasing the bias from the training data. Also, as an example shown here, when there are no stragglers, it performs reasonably well. When 90% of the device is slow, the method will not converge. And so fat average is a heuristic method in general, and it is not guaranteed to converge in practice. And to address these issues, we propose FedProx, which is a framework for federated optimization. And in particular, we modify the local subproblem by adding a proximal term. So here, WT is the current global model at the Tth iteration, and WK is the current local model at the Kth device. So this proximal term aims to penalize the large deviations of the current local model, WK, from the global model, WT. And mu is a constant here that controls how much we like to impose such a constraint. So this proximal term explicitly limits the impact of the heterogeneous local updates, and it allows us to analyze this method theoretically. Instead of dropping those stragglers, FedProx allows to incorporate those partial work. So it will aggregate whatever partial updates that are sent to the server before the given time window. So it will also aggregate those variable amounts of work from all the selected devices. And this term allows to safely incorporate those noisy updates. And we see that FedProx is a generalization of fat average, and it will reduce to fat average when mu is 0 and when there's no systems heterogeneity in the network. And we can use any local solver to solve this modified subproblem. And also, it comes with theoretical guarantees under a device dissimilarity assumption. So at a high level, we show that FedProx converges despite the heterogeneity. And in particular, we introduced the notion of the speed dissimilarity to characterize the statistical heterogeneity in the network. So we see from this formula that when the data are perfectly IID, B will be very close to 1 because those local gradients will be very close to each other and also close to the global gradients. And when the data are becoming more non-IID, those local gradients are differing from each other. And so B will be larger than 1. And the more non-IID the data is, the larger B will be. So we also assume that this dissimilarity metric B is bounded throughout the training process. And this metric has, which is interesting, that this metric has also been used in some other contexts, such as the gradient diversity, for very different purposes, like to quantify the benefits of scaling mini-batch distributed SGD. And so here are our final convergence results. And informally, we to obtain suboptimality epsilon, we need T communication rounds where T is basically 1 over epsilon. And rho is some constant that incorporates the dissimilarity metric B and the mu constant and some other constants. And the rate is general because it covers both convex and non-convex loss functions, and we can use any local solver to solve that local problem. And it is the same as standard distributed SGD, but in practice, it can converge much faster than distributed SGD. So, and our purpose for the analysis here is not show the optimal of the convergence rates, but also, but rather to show that first, FedProx does converge, and second, it is important to think about the convergence of federated optimization methods, considering practical heterogeneity assumptions. And so next I'll show some of the empirical results. So are there any questions?
Yes, there's one question from Tian. I will try to unmute you. Yeah,
Hi.
so please go ahead.
Thank you. So this result is for the deterministic setting with strongly convex.
Oh, this is for stochastic settings.
Setting and
yeah.
Strongly convex.
Not strongly convex. Like the original function, like before you add in that proxy term, that function can be convex or non-convex, and we assume that after adding that proximal term, the local problem becomes convex.
Okay. Okay. Thank you.
Yeah. Thanks.
There is one other question in the chat from Anupam. You can go ahead, ask, please. Or I can read it out loud. So the question is, how do you calculate B?
Yeah, that's a good point. So B, we just directly calculated B as the way that it is defined. And so we need to, for the purpose of analysis, we need to communicate with each device in the network too, and to calculate, to compute the gradients on all the devices, to get the local and the global gradients to calculate B. And in the optimization procedure itself, we don't need B. And in the analysis, we need B to somehow to show how the statistical heterogeneity changes during the training process, and to see how that is related to the actual convergence performance. And I think a very interesting future work will be to have such statistical heterogeneity diagnostics a priori, like to have some understanding of the underlying structure of the data of the network, and to have some estimation of that in a very efficient way before training. And somehow we can use, maybe we can use that to improve the convergence behavior of our methods. Yeah.
Also, I would have one other question with respect to the parameter mu. So do you assume this to be like a given, or do you have any like constraint for mu in order to your algorithm to converge?
Yeah, in order for the algorithm to converge, mu must be sufficiently large. Like it must be larger than some constants to make sure that the method can converge theoretically. And in practice, we in this work we tune mu from some like a few candidate values, and we keep mu fixed throughout the training process and across all the devices. But you can you can use device-specific mu's and to dynamically change mu based on the current behavior of the model.
Also, like one other question, because you said that your model or your algorithm can handle actually also like a partially solved local problem. So do you have actually, do you have any constraint like how good the solution needs to be, or it can be anything and you can still guarantee the convergence? This local, like a local solution, the solution of the local problem.
Yeah, so we can have arbitrary local solutions, and because the suboptimality of parameter of solving that local subproblem is also a parameter in the final convergence rates. So if you solve that local subproblem better, and the constant in the final convergence results will be better. And if we only solve that in a very inexact way, then the final convergence will also be affected.
Thank you.
Thanks.
It seems there are no further questions, so you can continue.
Okay. So yeah, so here are some of the empirical results. And we first look at FedProx in a setting without any systems heterogeneity.
Could I have one more question?
Oh, sure.
Apologies. I just wanted to see how is what is the dependence of B on the in the previous result that you have, in the complexity result. It's hidden somewhere in row, I presume. Yeah. Yes. So could you shed some light on the dependence? How does row depend on B?
So when
is it linear dependence or quadratic dependence, or what kind of dependence on B?
Have some backup slides just to show you the final convergence results. Yeah, so it's a little bit complicated, and so it's not. I think it's quadratic. Yeah, it's more a quadratic one, and there's some linear terms and quadratic terms. It's more quadratic. Right. Yeah.
Okay, so if I understand it correctly, this B, for instance, in the quadratic case, if your losses were quadratic, then B would be condition number of the problem, or at least largest eigenvalue or something like this of the matrix.
Yeah.
So quadratic dependence would be like a square dependence on the condition number, correct?
Yes.
Okay, just wanted to clarify that. Thank you.
Yeah, thanks for pointing it out. Yeah. So where's so when they're so for the empirical evaluations, we're using the Federated learning benchmark we developed at CMU called LEAF, and it includes some of the data sets with natural data partitions across different devices. And here we are looking at the results from the Shakespeare dataset, and it's the complete works of William Shakespeare and each device in this dataset corresponds to a speaking role in the play. And the task is next character prediction. And we have x-axis here to be the number of communication rounds, and the y-axis to be the training loss. And the origin line corresponds to Fed average. As you can see, in the presence of statistical heterogeneity on Fed, convergence is very unstable, and the method can even diverge. And this blue line corresponds to FedProx, and FedProx with mu larger than 0 leads to more stable convergence. And next, we'll look at results in the settings with high system heterogeneity. And we simulate the system's heterogeneity by randomly assigning variable amounts of work to the subsampled devices at each round. So the original method, FedAverage, is performing even worse. And FedProx with mu equal to 0 allows for variable amounts of local work to be performed locally. And that helps convergence. And further, if we add this proximal term, FedProx with mu larger than 0 leads to better convergence. And this is true for all the data sets we looked at. So I'm showing here the training loss, but in terms of test accuracy on average, FedProx achieves 22% absolute accuracy improvement compared with FedAverage in highly heterogeneous settings. And in the previous results, the statistical heterogeneity for the dataset is fixed. And to investigate the impact of that, we create some synthetic datasets which allow us to manually tune the degree of statistical heterogeneity. So from left to right, the degree of heterogeneity is increasing and the convergence is becoming worse. And however, setting mu to be larger than 0 can help to combat this. So the takeaway for the first part is that heterogeneity can lead to slower convergence, reduced stability, and even divergence for federated optimization methods. And it is important to analyze and evaluate federated methods with practical constraints like non-IAD data, expensive communication, and variable device participation. And due to the high heterogeneity, the performance of the devices may also vary a lot. So from a service provider's perspective, it is also critical to ensure fair quality of service for all devices. So the next question we ask is, how can we equalize the performance across devices in federated networks? And normally we solve this traditional empirical risk minimization objective for federated learning. And however, minimizing such an aggregate function may disproportionately advantage or disadvantage the performance on some devices. There are no accuracy guarantees for individual devices in the network, and the model performance can vary widely. And for example, here we show the test accuracy distribution of all devices from a model trained in a real-world federated dataset. And a small group of devices suffer from low test accuracy. And therefore, the question we ask is, can we encourage a more fair, that is a more uniform distribution of the model performance across devices? And the fairness definition considered in this work is the uniformity of the performance distributions. And so our goal is to reduce the variance of the model performance by increasing the performance on the worst performing group of devices. And we propose an optimization objective that addresses fairness issues. And so our QFFL objective minimizes an aggregate real-weighted loss parameterized by Q, such that the devices with higher loss are given higher relative weight in this overall objective. And it's called Q Fair Federated Learning, or QFFL. And this objective is inspired by alpha fairness for resource allocation in wireless networks. It enables flexible fairness accuracy trade-offs through this tunable parameter Q. So when Q is equal to 0, it recovers the previous ERM objective. And when Q is large enough, it reduces to the classic minimax fairness, where the goal is to minimize the loss of the single worst performing device. And in terms of theory, we have some generalization guarantees for QFFL. Also prove that increasing Q results in more uniform accuracy distributions across the devices in terms of the uniformity measures we define, such as variance of the loss. And for example, on the example shown before, due to the variation in the data across the devices, the model accuracy is poor on some devices. And if we're using QFFL, we can maintain the same overall average accuracy. We're reducing the variance. And we see that the performance of the worst performing device has improved at the cost of potentially reducing the best performing losses. Yeah, so here are our main empirical results. We're using LEAF still, and we see that on the 4 data sets, by using QFFL, which corresponds to red shown here, the performance distribution is more centered, which means that the variance has been reduced. And we can maintain the mean of the distribution. And on average, by using QFFL, we are able to cut variance of accuracy by 45% while maintaining the average accuracy of the devices. And besides fair federated learning, it is also possible to apply this QFFL objective to other settings such as mental learning. For mental learning, for example, we can do the same reweighting on the mental gradients to encourage more fair models across different tasks in mental learning after some few shot adaptation. And we have some preliminary results for that, and more investigations are left for future work. So more broadly, QFFL can be viewed as a generalization of minimax fairness, and that can be more efficient than solving a minimax optimization problem. And so QFFL can be used as an alternative when minimax optimization is hard to solve. And it can also be potentially applied to many other minimax problems. And so the objective described before can encourage a flexible fairness accuracy trade-off. And to solve this objective, we also developed some lightweight, scalable, and efficient solvers tailored to federated settings. And there are several challenges there. And first is that in order to trade fairness between accuracy for different applications, sometimes we need to train a family of objectives with different values of Q. That's sometimes we need to tune the hyperparameters for each Q. And also federated networks are heterogeneous with extremely expensive communication. So at a high level, to address some of these practical challenges in federated settings, we dynamically estimate the step sizes with different Qs to reduce the overhead of tuning the hyperparameter Q. And also our method allows for low device participation and local updating, which have been commonly adopted for federated optimization methods. So to adaptively set the step sizes for different Qs, we first hand tune a good step size on Q equal to 0, that is on Fed average. And then we estimate the global Lipschitz constant of the gradients on that objective. And we directly estimate it to be the inverse of the step size. And having this, we can estimate the local Lipschitz constant on any objective with Q larger than 0 at any point. And so this is a heuristic to dynamically set the step sizes for different Qs. And we empirically show that this can approximate a best tuned step size. So for example, in this figure, the blue line Q Fed SGD, which is our solver, is same or even better than a best hand-tuned Fed SGD with the best step size for solving the same objective. And so having this, we first describe a version of the solver without local updates. So at each round, the server first samples a subset of devices and then sends the global model to the devices. And those are common steps for federated learning. But each selected device K computes the gradients of the new QFFL objective instead of the original objective. And they also compute the estimated local Lipschitz constant at any point W. And the server will send the gradient and estimated constant to the server. And the server will update the global model using the estimated step sizes. Yeah. So to extend our solver to handle high communication with local updating, so we do a simple twist on QFET-HGD. And the basic algorithm is the same as before, but here instead of running a step of gradient descent locally, we let each device solve FK exactly by running many local updates to obtain a new model. And then we plug in the delta of the local updates as the gradient before. And so this is our QFET average algorithm. And we show that the local updates used in QFET average cause the method to converge faster than QFET-HG in terms of the communication rounds. So here the red line is QFET averaging, which is a communication efficient variant of our solver. And it is, in most of the cases, it's converging much faster than QFET-HGD. Yeah, so this QFFL objective also gets us to think about another objective, which is a reformulation with the same intuition. So we call it tilted empirical risk minimization. And the traditional, so the traditional ERM is minimizing the mean of the losses. But here the tilted ERM term is minimizing the exponentially tilted average of the losses. And so here the lowercase f xiw is the loss, is the traditional loss on sample xi with the parameters w. And we see from this objective that we are doing an exponential tilting on this original loss. And the parameter is t, so t can be both positive and negative. And when t is set to be positive, then the large losses, which is large f, will be upweighted exponentially in this objective. And when t is negative, small losses will be upweighted. And this has practical benefits of either promoting fairness using a positive t or mitigating outliers using a negative t. So there's a toy example on a linear regression task. So when the purple line corresponds to the case of t equal to 0, and that is the original problem of ERM. And when we set t to be positive, the solution will be fair to all the data points in the sense that it will impose small weights on the samples with larger losses. And when t is negative, as shown in blue here, this objective will overfit to the majority of the samples. So if those minority samples are considered as outliers, this objective has the benefit of removing outliers.
Can I have one question here? So isn't that a problem that this, if I'm not mistaken, that this like tilted empirical risk minimization is not separable with respect to data points? So isn't it a problem to actually compute stochastic gradient?
Yes, that's a very good point. So it if we directly calculate the grade, if we're using gradient-based optimization methods, because it's not separable in terms of the data points, and it's not clear how to directly solve it in a stochastic way. And we have some kind of dynamics or heuristics to dynamically track some of the terms in the stochastic solver to approximate that in the full batch setting. Yeah.
Thank you.
Thanks. Yeah. Because if you compute the gradient of this objective, the denominator will be the sum. Like you basically need all the loss information from all the samples in the denominator of that of the weight of the gradient. So we have some ways to track that dynamically in the training process. Yeah, so at a high level, this objective can be used to reweight samples to magnify outliers or promote fairness. And it provides a nice trade-off between the average loss and the max loss for positive t's. And also it is an approximation of some other estimators when the mean of the losses is not what the practitioners intend to optimize. And so it can approximate value at risk or super quantile methods where the goal is to solve a specific quantile of the losses. And so if you're interested, you can check out our recent paper on arXiv. So the takeaway for this part is that in heterogeneous networks, vanilla ERM may deliver poor quality of service in heterogeneous networks. And QFFL term allows for flexible trade-offs between fairness and utility, and they can also be used to other settings beyond federated learning. And so lastly, I'd like to briefly mention some of the future works. So as we mentioned before, for the FedProx framework, we use the bit dissimilarity as a metric to characterize statistical heterogeneity, but that is expensive to compute. So it will be interesting to study such diagnostics, to study if such diagnostics exist, and can we obtain that before training in an efficient and privacy-preserving way? And also, can we use that heterogeneity diagnostics to improve the performance to training? Like, can we use that to guide us how to sample devices, for example, in the training process? And in terms of the fairness, it's interesting to study the interplays between fairness and some other important metrics in federated learning, such as privacy or robustness. And also, it's interesting to look at the connections of our notion of fairness to other broader definitions of fairness in the machine learning literature. Yeah. And in our recent white paper, we have discussed some more challenges and the future directions in this area. So thanks. That's all I have. You can find all the papers, the code, and slides on my website.
Thank you very much for a wonderful talk.